Internet Protocol version 4 and Internet Protocol version 6. So when we have two devices that want to communicate on the network, they need logical addresses so they know how to address each other. So most modern networks we have are going to use what's called Internet Protocol, and the most common one that we use right now is version 4. We've been upgrading to version 6 for about the last 10 to 15 years, but we still use version 4 as a primary means of communication. The majority of our networks do use version 4. We are migrating up to version 6. And the reason why is because we're running out of available addresses. With version 4, it's only a 32-bit address, which means there's only 4.2 billion IP addresses available, which sounds like a whole lot, but when you start looking at the amount of devices that are on the network now, it's not enough. If you think about it, I'll look at myself. I have a laptop and an iPhone and an iPad. I have a streaming media box. I have a file server, I have a desktop, right? That's 5, 6, 7 computers that I have, right? There's 8 or 9 billion people in the world. There's not enough addresses for everybody. So we're doing a transition into IPv6, which is a 128-bit address, which actually gives us enough IP addresses for every man, woman, and child on the planet to have like a couple million each. I mean, it's just an exorbitant number that we should never, ever run out of. So they say. But we always end up running out of stuff eventually, right? We never thought we were going to use 4.2 billion IP addresses with IPv4, and here we are running out of IP addresses. So we'll talk more about that as we go through. So with IP addressing, our IPv4 is a 32-bit address. And the way we write this is in what's called dotted decimal notation. So an example of that would be you'd see an address like this, 10.1.2.3, or 192.168.1.1. Those would be a full IPv4 address. And the reason why they're called dotted decimal is they have 4 decimal numbers separated by dots. Each of those numbers is what we call an octet. So the 10 is the first octet, the 1 is the second octet, the 2 is the third, and the 3 is the fourth octet. Each of those octets are actually 8 bits long if we wrote it in binary. So for instance, if I wrote 10 in binary, it's actually 00001010. If I wrote 1 in binary, it would be all zeros and a 1. Okay, you can see how it breaks up into that. For A+, you don't need to know how to convert things from binary to decimal and decimal to binary. When you get into Network Plus or Security Plus, there are some questions that might require that. But for A+, you won't need to. The big thing you want to take away from this is that it's an IPv4 is a 32-bit address. And that we write this, each of these are called octets, each of those dotted decimal parts. So with IPv4, we can actually break down our addresses into what we call the network portion and the host portion. And the way we do this is based off subnet masking. And so the reason why the binary becomes important is when we use it, anytime we see the 1, it locks that network part in place. Anytime we see the 0, that defines the host place, as you can see in this chart below. So normally you'll see the IP address like 10.1.2.3, and in coordination with that, you'll have what's called the subnet mask. So in this case, we have a 255.0.0.0. And by doing that, the 255 in binary is actually all 1s, and the zeros are all zeros. So the host is, this is the 10 network. So anything that has an IP address that starts with 10, so 10.something.something.something is going to be on this particular network. The host is referencing the exact computer you're dealing with. So Sarah's computer might be the 10.1.2.3, where Nick's computer might be 10.1.2.4. They're both on the same network, on the 10-something network, but they're individually identified. If you think of this like a phone number, right? Your area code references that whole city that you guys are all in. That's that network. And then your actual number identifies you, right, in your house. So we have 3 classes of IPs that we talk about with IPv4. We have Class A, Class B, and Class C. And what defines them as A, B, or C is the subnet mask and what the first number in the first octet is. Okay? So for Class A, it's going to be anything from 1 to 127. Those are all Class A addresses. And so here we start with 114, which means this is a Class A address. And the typical Class A subnet is 255.0.0.0. And I'll show you a chart with all these again to make it easier for you. But as we look and we want to define this, like I said, the 255 defines the network part. So this is the 114 network. So you'll see it's the 114 network, and the host that we're talking about is the 114.56.20.33 host. With class B, we're going to be looking at the fact that there's two 255s, so the first and second octet would be our network, and the second two octets, the last two octets, are going to be our host. For class C, we have 255, 255, 255, 0, so that means our first three octets make up our network, and our last one makes up our host. Okay, and I'll show you why that's important here in a second. So for each class of subnet, we have a default subnet mask. And for the A+ exam, we're only going to worry about the default subnet masks. We don't need to worry about breaking these into smaller networks. We'll get into that when you guys go into Network Plus later on. So with class A, for class A networks, our first value, our first octet, if it's between 1 and 126, it will be a class A network, which again has the standard 255.0.0.0 subnet mask. For B's, we have 128 through 191, and that means we're going to have a 255.255.0.0 as our subnet mask. And for class C, we're going to have 192 through 223, and that gives us 255.255.255.0 for our subnet mask. It's important to know what is a class A, B, and C network. You may get a question on the exam that says, you have an IP address of 172.13.4.8. What class is this? That would be a class B because 172 lies between 128 and 191, right? So you want to make sure you understand the class and the value. The easy way to remember the subnet masks is A is 1, B is 2, C is 3. So A's have 1 255. B's have 2 255s, 255, 255, 0, 0. C has 3 255s, 255, 255, 255, 0, right? So 1, 2, 3, A, B, C. Okay, that's the way you can remember that third column there. But you do need to remember these numbers, 1 through 126, 128 to 191, and 192 through 223. If you're wondering why 127 was skipped, notice it's not there between A and B. It actually is a class A address, but it's skipped because it's reserved. You can't use that IP. It's reserved for the loopback. And what the loopback means is this is my IP. This is my computer. All computers, if you go to the 127.00.1, will bring you back to yourself, okay? In addition to whatever your routable IP is. That's just a standard one that has been saved for that purpose. So we also have these things that are special IP, that are IP address classes that are not publicly routable. They're called private. So when I have an IP address, I need a publicly routable IP so that I can go over the internet. Okay? To get one of those, you have to pay money to your internet service provider. When you're at home, unless you're paying extra money, you get what's called a dynamic address. It changes on you all the time. So if you have a Verizon connection, Verizon gives you an IP and you can use it for a couple of days and then they're going to switch it up to a new one. If you wanted to run a server, that would be bad. That would be like moving your house every 3 days, right? It'd be really hard to come over for dinner. So we want to have the same place all the time. So if you want a static IP address, you pay extra money for that to Verizon. And they'll go through ICANN and they'll get you an IP address and you'll own that IP address. And now you'll have the same phone number or the same address every day. So you have to purchase those. Most of us aren't running servers from our house though, so we don't need a public IP address like that. So instead what we do is Verizon gives us this dynamic one that we can borrow 3 days at a time. And then inside of our network, we will actually use what's called private IPs. And private IPs, I like to think of them like pet names, right? Like you and your spouse may have pet names for each other, but nobody else calls you that. And if somebody did, you'd be like, huh, that's kind of weird, right? So your private IPs can be used by anyone, but they're only routable inside your local network. So for instance, my laptop, if it's using the private IP of 10.1.1.2, when it goes onto the internet, it needs a public-facing IP, which it gets from Verizon. It uses that and comes back. But if we're going to talk here locally, I can use those local addresses. And the way we do that is what's called network address translation. Okay? For each class of IP, we have a range that's set aside that are private IPs, meaning anyone can use them without having to pay money. But again, they won't be able to go on the internet with these. So you have class A. Anything that starts with 10 is going to be private. Okay, notice 10.0.0.0 all the way up through 10.255.255.255 are all private. Okay. With B, If it starts with 172.16 through 172.31, those are all private. Okay, so you got to make sure you know those as well. That's the difficult range because it kind of starts in a weird place, right? It's not just anything with the 172. Because if I gave you 172.12.something.something, that is public. But if it's 172.16 or 172.17 all the way up through 172.31, that's private. And then the other one that's fairly easy to remember is Class C, 192.168 something.something. Okay? It starts with 192.168, it's private. Why is this important? Because you may see a question on the test that says something like, if you have the IP address of 192.168.1.3, what class is it? It's Class C, right? Or is it private or public? It's private, right? So you have to know those from that perspective. So this chart here is important for you guys to learn as well. We also have two special IP address ranges. We already talked about the loopback one. This one is the one that starts with 127. 127.0.0.1 is the loopback address. It references your own computer and it's used for local testing. The other one that is special is what's called IPEPA, which is kind of fun to say. It's an acronym inside of an acronym. It stands for the Automatic Private IP Address. So gotta love acronyms inside of acronyms. Automatic Private IP Addressing. And anything that starts with 169.254 is an IPEPA address. So we'll talk about DHCP in a minute, but essentially what DHCP does is when you turn on your laptop, if it's in DHCP, it stands for Dynamic Host Control Protocol. It's going to dynamically be assigned an IP address by your router. And so what happens is your laptop turns on and it connects to the router, and it says, hey, I need an IP address. And so the router will go, okay, you're going to get this IP address, and it gives it one. Well, if your laptop can't make connection to the router because maybe your cable's bad or you're having interference, it won't be able to get an address. And it would end up causing Windows to basically sit there and crash if it just kept looking for an address and didn't get one. So what they've done is they've programmed in, as part of the DHCP protocol, that if it can't get an address within a certain amount of time, it gives up and just picks a random address. And that random address it's going to pick is going to be a 169.254 address. Okay? So it'll just be something. Now the problem with an IPEPA address is you can't get on the internet with it. You can't get on the network with it. You're just sitting alone in yourself. Your computer just gave up and couldn't make a connection. Okay? So if you ever do, as we go through troubleshooting, you guys will see this. Anytime you see a 169.254 address, that means that you don't have a network connection. Okay? Even though you have an IP address, it's not valid. Okay? So we'll talk more about that later as we go through. So subnets. Why are subnets important? Like I said, for this particular class, you don't need to worry too much about subnets. The only reason I'm bringing it up is just to give you some ideas of why these subnet numbers are important. Okay? As I said, class A, B, and C is like 1, 2, 3 with the number of 255s. If you look at this, you can see the fact that we have a class A address. Its network was the first octet only, meaning there was 3 octets for the host. Each octet can have a number between 0 and 255 in it, giving you 256 combinations. So if you had a class A address, you can actually have up to 16.7 million computers on that network. That's a pretty big network, right? Do you need that much for your home address? I don't think so. I don't even need that much, right? How about class B, right? If we look at class B, we have those 2 zeros, meaning we have 2 sections that can be hosts, which is 256 times 256, which in this case gives us 65,000 IP addresses. Still a rather big network, right? We go down to class C, and we have 256 addresses. 2 of them aren't usable. We're not going to get into that right now. But you essentially have 254 computers that can be on that network. So when you go to your house, you have a private IP scope established by Verizon. Generally, Verizon uses the 192.168, which is a class C address. So you can have up to 254 computers on your Verizon connection. Okay? If you use Comcast, they actually use a 10 scope. So it's actually a class A IP address that they're giving you, scope for their private range, which means that you could have up to 16 million addresses on your router. Now your router would crash because it's not designed for that. And what they do instead of using this 255.0.0.0 subnet mask is they actually subnet it down and they use this 255.255.255.0 subnet mask. Meaning that even though it starts with a 10 and it's a class A address, they're going to subnet it and cut it down so it's only looking at it as if it was a Class C address from a sizing perspective. That's what a subnet allows us to do. It allows us to take a big area and cut it down smaller. So for instance, in our classroom, we've got 12 desks on the left and we've got 8 desks on the right. I can actually subnet out and say, you know what? I don't need one classroom with 20. I need one classroom with 12 and one classroom with 8. And I can break us apart into 2 different networks inside of here, 2 sub-networks inside the one big network of this classroom. Does that kind of make sense? A little bit? All right. The other good thing about that is it gives you separation of networks for security control. Because if I broke the classroom in half, the guys on the right can only talk to the guys on the right, the guys on the left can only talk to the guys on the left. And so we can keep you guys broken up and also give us better bandwidth control. So that's the idea of a subnet. Again, for A+, subnets are not covered in depth. If you really want to learn all about subnets, if you go into a Cisco class or you go into Network Plus, you'll learn really in-depth stuff about subnets. And if you're really interested, I do have videos on subnets in my Network Plus lectures online, so feel free to go check those out as well. So with IPv4, there's 3 ways that we send data. The most common is unicast. So when you go onto Facebook, for instance, you go to a server and you say, hey, give me my Facebook status, and it sends it back to you. Unicast, it goes from one source to one destination. So in this case, if we have 3 students here, receiver 1, receiver 2, and receiver 3, and they're all getting information from the Facebook server, the one's destined for receiver 1 goes to receiver 1, the one destined for receiver 2 goes to receiver 2. And the way it does this is based on the destination IP address, which is your workstation's IP address. The second way we can send data is what's called broadcast. And this is where we send data from the server to everyone on the network. Notice it went from the server to the switch, and then all 3 of them got a copy of it. That's a broadcast message. Okay? Data won't travel past routers in broadcast, but it will go to all devices on our network. The third way is what we call multicast, and this is usually used with streaming video. Essentially what happens is these receivers both tune into a certain channel, if you want to think of it that way, by sending a join message to their switch or router. The server then sends the information to that switch or router, who then sends it out to those who join that network. In this case, we have one message going from the server to the switch, and then from the switch, it copies that message twice and sends it to receiver 1 and receiver 2. Receiver 3 didn't ask to be part of it, so he didn't get a copy of it. This is really good for live streaming video services. Okay? So if I was going to do like a video webcast over YouTube live streaming, and 7 people wanted to get that information, I send it out once and then all 7 get it, instead of me having to send it out 7 individual times like I would with unicast. The ways we assign IP addresses, we can do it either statically or dynamically. When we do it statically, it's rather simple to do, but it's very time consuming. It's also prone to human errors and impractical for large networks. So for instance, in this classroom we have 20 machines. If I wanted you guys to statically assign the IPs, you would have to go as an administrator onto every machine and set up the computers and say, this one's going to be 192.168.1.2. This one's going to be 1.3. This one's going to be 1.4. And you'll go to every machine individually to do it. It takes a lot of time. For 20 machines, that would probably take you 20 or 25 minutes, right? Let's say I had a network with 5,000 machines. That would take you a really long time, right? When I worked in the Middle East, our network was done statically, and we had over 5,000 machines at the time I was there. It was a nightmare, okay? And what happens if I have 2 computers that have the same number? IP conflict, right? And it doesn't work right. So in this class, we have 2 NICs. If I yell out Nick, they both go, what? Right? So we have to say, hey, Nick this and Nick that, right? Or Nick front row, Nick back row. So that's the problem with static, is it's prone to human errors. Because if you skip a number or you use the same number twice, you're going to have a lot of problems. Dynamic, on the other hand, is much easier. You set up the server and say, here is the scope of IPs. This is the range I'm going to give you. Here's the 200 IPs I want you to hand out. And what happens is when the computer turns on, it goes, hey, server, I need an IP. And the server goes, okay, you can have the first one. Next guy, you can have the second one. Next guy, you can have the third one. When you're done, he'll take that IP back. Okay? And that's what you use usually for large networks. It works a lot better. It is a lot less confusing, and it is a lot quicker. When you assign an IP address, you have to assign 4 things at a minimum to get a valid IP address set on your network. The first one is you have to have an IP address itself, right? So the first box you'll see here, we have the IP address, 200.200.200.5. You'll see we had to put in a subnet mask to define what network it's on. It's on the 255.255.255.0 network. And then I need to have the gateway. The default gateway is actually the router. How do I get off this network if I want to go talk to the internet? In this case, the router's IP is 200.200.200.10. Okay? And then you need a DNS server. And what a DNS server does is it converts names to numbers. So when you go on the internet, you want to go to Google. How do you get to Google? Type in google.com, right? You don't type in an IP address. But computers don't understand names, they understand numbers. So what DNS does for you is it does a lookup and it goes, okay, if you want google.com, that means you really want 8.8.8.8 or whatever the IP address happens to be. So your DNS server is a server whose whole function is to convert names to numbers and numbers to names. If you don't have a DNS server or your DNS server is not working and you try to go to google.com, it's going to come up with an error because it's not going to know how to get there. Where you can still get there if you use an IP address, you just can't use your names anymore. WINS is a lot like DNS, but it's for NetBIOS, which is internal networking for Windows. It's how you find network names or server names on your network inside your local network. And so you don't have to have WINS configured, but in large corporate environments, you generally will. In your home network, you're not going to have a WINS server, but you will have a DNS server. Okay? And if you don't have one, your DNS server is actually set to your cable modem or fiber internet provider like Fios or Comcast. They'll provide DNS for you as part of your package. But again, if you want to make this easy, you just go ahead and do DHCP and it will do all the self-configuration for you, which is what you're probably using in your home networks right now. So 2 ways to do dynamic configuration, the old way and the new way. The old way was bootp. You won't see this out in the field anymore. Back in the day, we used bootp. It did dynamic addressing for you. It assigned an IP, a subnet, and a default gateway. What was it missing? DNS, right? No DNS server. So it didn't work well with us all moving to the internet and using domain names. So DHCP upgraded bootp. It added in the DNS server as well. And if you're using voice over IP, it does have the ability to send out the parameters for that as well. DHCP is what you're going to run across all the time in the field. It is what we use on like 95% or more of the networks out there. If you want to do dynamic, you're going to be using DHCP. So, as I said before, we started running out of IPv4 addresses because we have so many network devices and wireless devices now. Because of that, we had to upgrade our addressing scheme. We talked about in IPv4, we're using 8 bits times 4 octets, giving us 32 bits of addressing. IPv6, on the other hand, has 128 bits, which gives me 340 undecillion addresses, which is 5 times 10 to the 28th power. That's a 5 with 28 zeros for every person on our planet, not plant, on the planet. Some people always ask me, you know, what about IPv5? What happened to that? It was a 64-bit addressing scheme. It was experimental. They took a lot of the stuff from IPv5 and just merged it into IPv6 and released it. IPv5 was only experimental. It never made it into the main marketplace. So what you'll run across is IPv4 or IPv6. So IPv6 benefits over IPv4. Why did we go to there? Well, the biggest one is we have a much larger available IP address pool. Again, 5 with 28 zeros after it for every single person on the planet. That's a big number, right? There's no broadcasts. So that broadcast where I send it once and it goes to everybody at the same time, that was taken away. Something from a security perspective, there's no packet fragmentation. And really what that means is with IPv4, I could send you say I was going to send a book to you in the mail, but it's too heavy to put in one envelope. I could break it apart into multiple envelopes and send it that way, right? That's fragmentation. With IPv6, we just make bigger envelopes if we need to, so we don't fragment it. The reason why is a lot of bad guys started using fragmentation against us. A lot of our security devices, when they're looking for something bad, like a piece of malware or a virus, they look at the whole thing and go, that looks bad. But if I look at it in pieces, it doesn't necessarily look bad, right? And so fragmentation could get things snuck through before. And so with IPv6, they took away fragmentation. They say, we'll just make bigger envelopes. It can coexist with IPv4 during transition. So we have been transitioning for a long time. We were supposed to go to IPv6, it was like 2005 or 2007, and get rid of IPv4 completely. It still has not happened. We're still using IPv4. And so right now we can run dual stack where we're running IPv4 and IPv6 at the same time, or we can run IPv4 on top of IPv6 on top of IPv4 as well. For us as A+ technicians, it doesn't really make a big difference for us. The fact is, we have the ability to do both right now. It also has a simplified header. So instead of having 12 fields like we have in IPv4, we only have 5 fields. Less information is required to actually make things send back and forth. Again, when you get into Network Plus, you'll actually look at the headers and determine what's in there. For this class, we don't need to worry about that. It's way beyond the scope. Big thing for us is that there's a lot more IP addresses, okay? So the types of questions you're actually going to see on the exam about IPv6 specifically is going to be about what does an IPv6 address look like. They may give you A, B, C, and D and say which one of these is an IPv6, okay? IPv6 is a little bit harder to read. They're written in what's called hexadecimal. So it uses the numbers 0 through 9 and A, B, C, D, E, and F. Okay? That represent 0 through 15 is the number scheme for it. And so, for instance, IPv6 can look like the one on the top. That is a full IPv6 address. But we can also summarize it down. So if you see 4 zeros, if you thought about it in our normal numbering system, is the same as 1 0, right? So you can do the same thing. So we can take that top one and summarize it as the second one. It's the same number, just shorter. The other thing you can do is if you have multiple repeating zeros, like this, you can put a double colon in there once, and that represents all the extra zeros. So this top address is the same as this middle address, is the same as this bottom address. So if you have consecutive groups of zeros, you can omit them by using 2 colons, but you can only do this one time per address. And the leading zeros can always be omitted as well. So if you notice here, on this bottom address here, we have 0, 1, 2, 3. We can drop that 0. Or 0, 0, 0, A, we can drop those zeros and just become A. And as you see here, we have the A and the 123. And this group of all these extra zeros is just summarized as a double colon. Okay? So how do you know it's an IPv6 address or not on the exam? If you see numbers with letters and numbers, it's probably IPv6. The one exception to that is MAC addresses. MAC addresses are also written in hexadecimal. Okay? The big thing, though, is MAC addresses are always 12 digits. Okay? IPv6 doesn't have to be 12 digits. So if you see something that looks like this, it's IPv6 unless you count it and there's 12 digits. If there's 12 digits, it's a MAC address. Okay? The way we have data flows in IPv6, we still have unicast, just like we did in IPv4. One packet going to one receiver. Same thing here. The red one goes to the red, the green goes to the green, based on the address. The only thing that changed is the IPv6 address. Here it's : 2, here it's : 3. Multicast. We still do multicast, just like we did in IPv4. The only difference here, again, is our IP addresses and who they're going to, right? This is still a multicast group. These 2 guys have subscribed, so they're going to get the live video. The guy down at the bottom, number 4, he's not going to get it because he didn't ask for it. The third way is different. It's called Anycast. So we got rid of broadcast, and instead we use this thing called Anycast. And what it allows you to do is it's designed to let one host initiate efficient updating of router tables. And again, you're not going to see a question about this on the A+ exam. The idea here is that it actually travels from one server to the nearest of multiple locations and get to there based on what's closest to where it's sending it to. Okay? Don't worry much about Anycast and IPv6. Again, unless you go into the networking field, you're not going to deal with it. As an A+ technician, we're not worried about it. You're going to be dealing with unicast for almost all your communications, which is a one-to-one send. So which of the following is the number of bits that compromises an IPv6 address? Is it 32, 64, 128, or 256 bits? 128, right? IPv4 is 32, IPv6 is 128.